Hello. Today I'm speaking with Dennis Hadjivelichkov, who graduated this year from the Foundational AI CDT with an astonishing 13 papers, which must be a record of some kind. Welcome, Dennis.
Hi, I'm happy to be here.
Great to have you. So, the title of your thesis that you submitted this year was Semantic Correspondence in Robot Perception. Can you explain what that means in simple terms?
Yeah, sure. Semantic correspondence means identifying parts of different objects that are functionally or conceptually similar, even if they look different. In robotics, this allows us to understand that the handle of a mug and the handle of a kettle are both meant to be grasped, even though they have different shapes, different sizes, different colors. So instead of just matching things by appearance, the robots learn how to match things by what they are or what they are for. My research focuses on giving robots this ability so they can generalize skills like grasping, pouring, stacking to new unseen objects, just like humans do. If a robot can establish semantic correspondences, it can generalize new like behaviors to new objects that it has never seen before. It can recognize affordances, which means that it can recognize what an object affords to be done as an action. For example, parts that can be pushed, pulled, poured, and it can also transfer learned skills from one object to another based on this semantic shared semantic structure.
Okay, interesting. So, if I understand that correctly, you would be able to, using this method, you'd be able to train it on mugs with the handle of mugs, and it might then learn what a handle is in general, or at least that hoop kind of handle, and then be able to pick up a teacup or a kettle as well.
Yeah, there are different methods that look at this problem from different angles, different perspectives. But generally, yeah, what you described is one way of thinking about correspondences. You can train a model that specifically is trained to recognize um, the handles of mugs, and then you will be able to correspond that to new mugs.
So you were explicitly training in this semantic understanding, or do you hope it emerges from scale?
So in the first work of my PhD, we trained the model on point correspondences. So basically, if we have the tip of my shoe and the tip of your shoe, can we correspond them? And that model was trained on a large number of unsupervised data, so basically self-supervised data without any human annotation. Uh, Throughout the PhD, we pivoted towards using foundational models that can be used directly. They output semantic features, which naturally have this emerging ability to correspond to other key points that are similar. And we use those features to make use of them in robotics.
I see, I see. So you near the end, you were building on pre-existing foundation models?
Yes.
I see. Okay. So what were the key findings of your thesis?
Uh, yeah, so again, with my first work, what we did was we extended an existing method called dense object nets, which is a method for learning dense visual correspondences, and we made it, we we enabled it to distinguish between different object categories. So the base model that we started with was able to as I mentioned with shoes, it can learn how to correspond between different shoes, but within one model, you could only have one single object category, and we expanded that model, that method to learning multiple object categories within the same model without any human supervision, without any labels. And this allowed the robot to match objects and object parts across a wide variety of items, even in cluttered scenes. One key insight from this work was that point correspondences are tricky. So again, with the example of the points on the shoes, the tip of my shoe and the tip of your shoe, there is no ground truth correspondence between the two. If you think about it, there could be multiple ground truth correspondences. So reality is a bit more fuzzy than that. It's not a point-to-point correspondence.
So these point correspondences, if I understand correctly, this is when you have, say you have two shoes and you want to say which points on these two shoes are analogous. So the tip of this shoe and the tip of this shoe are
Yeah.
analogous, and maybe the end of the lace on this shoe and the end of the lace on this shoe are analogous. But there can
Yes.
be two different types of
Completely
shoes?
different shoes. Yeah,
I see. And so if the two shoes are very different, like a high heel and an ice skate or something, then you can't have, there's no ground truth about which points correspond to which other points, but you can still try and do the best matching possible.
exactly. Yeah.
Okay. And then how does the semantic aspect come into this?
So because these objects are completely different and the training is not done based on geometric properties, rather on purely visual semantic properties, that's why we call it semantic correspondence, because it's not geometric correspondence. It's not trying to find a particular point on the shoe that has a particular angle or something like that. It's a purely semantic approach in this case.
So this first work was on point correspondences. Can you explain what the second one was on?
Yes, sure. In our second work, we introduced a model called of course, short for affordance correspondence, which allows us to specify with just one example a specific part of an object that we find interesting for one reason or another. So, for example, this could be, again, with the mug, it could be a handle of a mug. We specified as a 2D part in an image. And then, given these semantic features that we're building on top of, which are based on Dino VIT, which is a foundational model, we're able to find correspondences of that particular part in a different mug. And this allows us to then use that in robotics. So in a way, we specify what we're interested in. The robot focuses on the part that it finds correspondence of, and handles it the same way.
Okay, nice. So what was it successful?
Yeah, it was pretty good. I think it is the first method that is able to do part correspondences from a single example.
Hmm.
Most methods before it have not really focused on that. They focus on full instance correspondence or other kinds of correspondences. But for part correspondence, this is the first work of its kind. And it was surprisingly successful.
And were all of these experiments in virtual reality environments, or were they? Did you try physical objects?
So we had a real data set that we were using for evaluation, which is called UMD. And I think we made a subset of that data set that is specific for our use case called UMDI. And we also tried this method on many different images, real and simulated. So we simulated some objects. We find correspondences from a simulated object to a real object, for example, or vice versa. So we had a mug, let's say, or some object where in which we know some part is interesting in some way. Let's say we have a handle, and we know how to handle that handle with the robot. So we have a grasping policy that can work on handles, even just given a 2D mask of the handle. Given that image that is taken from the internet, annotated by me, let's say, we find a correspondence of it in the view of the robot, and the robot can then act on the mask that it finds as a correspondence to the example.
Okay, okay. Yeah, it's really cool to be able to do something from a single image is pretty powerful, and you usually don't get anywhere near that kind of sample efficiency in robotics.
Yeah, it's very interesting. And we actually extended that work from 2 dimensions to 3D. And again, it worked from one or a few examples. It was just as good. And I think there's a lot of promise in the field for working with low data regimens.
Yeah, it sure sounds like it. So I think you were gonna go on to talk about some of your other work.
Yeah, sure. So after this 2 dimensional part correspondences, we extended that work from 2 dimensions to 3 dimensions. Basically, we showed that we can predict how two objects should be positioned relative to each other. So let's say you have a mug and a bottle, and you give one example of a mug pouring into a bottle, and then you give the model two different objects. So a different mug, a different bottle. It can predict where this relative pose between the two objects is that matches the example. So yeah, like that is obviously very useful in robotics, because as soon as you have something like that, you can then extend that to doing interactions. So that's actually what we did after that. We find some particular relative pose between two objects that is interesting. So let's say again with the pouring pose, we have some pouring pose that is just before pouring. We know how to align the objects in that way. So we send a command to the robot to align the bottle with the new mug in this way, such that it's just before pouring. And then we simply repeat the action of pouring. So whatever we've seen in demonstration, we repeat it.
Hmm.
And that is often successful.
So it was able to get the water in.
We didn't work with water because water is dangerous near robots, and like we don't really want to do that. So actually, I did work with bottles full of liquids,
Hmm.
but the cap of the bottle was always on, just to make sure there's no accidents.
But it would have got in.
Most of the time, yes, but there are definitely some failure cases. After all, we're working with a single example, and a single example, unfortunately, is not enough to fully specify a task. So, uh, if you, for example, I'll take this object as an example, right? We grasp this demonstration object here, right? When we have a new object that is similar but different, how do we know what is exactly the intention of this demonstration? Was the intention for us to grasp where just below this line is? Or was the intention to grasp this much distance above the bottom?
Hmm.
So just one example is often not enough. And that's one of the insights of this work, that basically we need to also in the future incorporate intent in this.
Right, right. So to understand the bottle example, um, there are many different ways in which the system could interpret what is a matching pose for a new bottle and a new mug. So it might be, oh, the bottle was meant to be this height above the table and tilted at this angle, or it might be that the mug was meant to be rotated this way rather than that way. And it's only by understanding the intent of the person holding the bottle and the mug that you realize, the orientation of the mug doesn't matter. The height of the bottle doesn't matter. It's only the fact that the water would go in the mug that
Yes,
matters.
exactly. So it is difficult. We pose ourselves with the difficult challenge of how much can we actually extract from a single example. And for simple pick and pouring and stacking examples, it was working fine, but obviously not always fine. Uh, for more complex skills, I think we need to incorporate this intent as well.
Hmm. Hmm. And that's something that can come from foundation models again.
Well, so we are building on top of foundational models. So we use the foundational model for vision, a vision backbone. I think
Mm.
the if we want to use something off the shelf for this rather than building it ourselves, we would need some sort of model that is capable of reasoning, which I don't know if we're quite there yet. A lot of people in robotics are using reasoning agents, and they're showing a lot of promise, but we're not there yet, and we might need our own robotics foundational model that does this, because we need to have a model that is capable of spatial intelligence, and a model that is trained on fully two-dimensional data may never be fully capable of that.
I see. And it's two-dimensional because you're just feeding it pictures rather than video.
Exactly. Yeah. So one
I see.
example of a failure mode of using this foundation model that we were using was if you have an image, a picture of a frog, let's say, and then a real frog, it might still find correspondences between the two, even though in 3 dimensions they are different.
Yeah,
And
yeah.
when you try to move 2 dimensions to 3 dimensions, these semantic features start actually leading you to failure cases because of these wrong matches.
Hmm. Hmm. I see. So if it was a 2D picture of a mug rather than a mug itself, it might start picking it up in completely the wrong place.
In that work, in the work in which we're doing 3D correspondence, we do have some safeguards against this, but it does make matching correspondences more difficult. So, for example, if you have a picture of a mug next to a real mug, these correspondences might fail you. You might
Hmm.
find the wrong object or the wrong part.
So my understanding is that a lot of your research in robotics was on transfer learning. And transfer learning is something that's plagued many other parts of AI when you're trying to transfer knowledge you've learnt in one domain or on one task onto another domain or another task. And it's sometimes been solved by enormous foundation models, such as the GPT series trained by OpenAI. So, do you think foundation models hold the same promise in robotics?
Yeah, so I think foundational models are great and they enable a lot of applications in robotics. As I mentioned, my own work was enabled by a large foundational model by Meta, which is Dino VIT. When it comes to large behavioral models for robotics, the story is a little bit different than those specialized in text or vision. Unlike with images and videos and text, where we have large corpora of data, with robotics, the data is limited. And even if you did have a lot of data and a model was trained on it, you may still have to fine tune it on your specific robot and use case. After every calibration of the robot is slightly different. It's not acting exactly the same. So you need to fine tune that model. And even if you can have this massive amount of data and you fine tune the model, you still need to ensure that this robot is safe for use in real applications. Because when you encounter an out of distribution case in ChatGPT, when someone types something really random and ChatGPT gives a bad response, it's okay. There's no danger. But when it comes to robots, it could lead to it could cost someone's life. So I think with robotics, it's going to be a very different future. Like we're due a foundational model moment similar to ChatGPT, but it might look different than the previous milestones. But it will be just as big, if not bigger. And yeah, because of these out of the distribution issues that we're experiencing, um, a lot of the big companies that are investing in foundational models for robotics, for example, Wave is making foundational models for self-driving cars. They have spent so much time making sure that the foundational model can cover and work better in this long tail of the curve, so long tail of the distribution of cases. Because if your car encounters a truck which has a stop sign attached to it at the back, you don't want your car to suddenly stop. You
Yeah.
want it to actually be able to navigate the situation just as a human would.
Yeah, yeah, and that's something that scale's not really going to solve because those instances come up so rarely. You could maybe solve it with scale by artificially creating lots and lots of data like that, but you have to be very intentional about it in a way that you don't really need to be with large language models.
Exactly. My honest opinion is that we need actual reasoning in for robots to work with foundation models in the real world. We cannot just parrot like other foundational models. And yeah, it's still unknown exactly how we'll reach that. There's a lot of different paradigms and a lot of different approaches. Some researchers think that you can just simulate the real world. So before you do anything, you can simulate exactly what would happen if you do this or that, and that's one way. I my bet is on reasoning.
And by reasoning, you mean incorporating large language models?
Uh, Large reasoning models, they don't necessarily need to be trained only on language. I believe they need
Mm.
to be trained on all kinds of modalities,
Mm.
but they need to be able to think, even if the thought process is not based on traditional language embeddings.
I see. So it could be in some mysterious latent space.
Exactly. Yeah, I'm not going to constrain the future. It could look like anything.
Yeah, I see. I see. I mean, this is more of a big open question in robotics rather than something we know the path towards.
Exactly. If I knew the answer, I think my PhD would look different.
So what got you hooked on robotics in the first place?
Uh, I think the journey to robotics was a little bit unexpected for me. So I started off in my childhood wanting to be an architect. I
Hmm.
spent all of my childhood basically drawing and in aspiring to be an architect. And then I was coming of age. I was nearing the university years, and I had to make a decision. And then I realized that there are so many architects around me. Basically, every third person I knew at my age wanted to become an architect. And the other two had a relative that was an architect. And my thought process was okay, if there are so many architects, but there are so few actually cool projects like these massive buildings, and there are so many dope projects, these tiny buildings, maybe like an outside bathroom or like a small cafe. um, I thought, okay, the chance of me becoming an architect that works on fun stuff is small, so I should pick something else. So I had 1 year, I think, to choose, and this was kind of a rash decision. I was going through the list of all types of engineering because I knew I want to do either marketing or some type of engineering. And my dad, who is a lecturer in marketing, he said, "You should not study marketing. That's not your thing." No, but to be fair, he didn't say it like that. He said that I don't want to. Maybe I don't want this to sound bad, but he said that any engineer can become a marketologist, but no marketologist can become an engineer. And that's how he pushed me in this direction of engineering.
Hmm.
Even though it's once you're in engineering, it's really hard to leave. Like you don't really want to become a marketologist, even though it really sounds fun. Um, yeah. So after that, I was looking through all the kinds of engineering, and the one that caught my eye the most was mechatronic engineering, which is a combination of mechanical and electronic engineering in one. Basically, high
Hmm.
level stuff like robotics, and that's how I got into this field. And then I worked as an engineer um, at ARM for 1 year. I was doing image signal processing. So basically, as a mechatronic engineer, you have opportunity to go in many different directions. You can go lower, doing electronics, control systems. You can go higher. You can do AI. And in that 1 year internship, I I had fun, but there was not that much work for me to do. I spent a lot of time next to the coffee machine waiting for more work to be given to me. And while doing that, I was teaching myself machine learning because machine learning was not part of my curriculum. And I found it very interesting, and that's how I decided. Okay, actually, like I think I want to work with machine learning. Specifically, I am very interested in computer vision. And my thought process was something like this: like if I want to work in computer vision, but I have a background in mechatronic engineering, I need to have this stepping stone in between. I need to do computer vision for robotics. And
Hmm.
this led me down this rabbit hole of the subsequent masters at UCL and then PhD.
So it's quite a strategic path you followed, but it seems to have paid off really well. I mean, it does seem like you found something you're extremely passionate about.
I don't know if okay. Yes, I am passionate about this, but I don't think passion is just simply an interest. I think passion is something you develop with experience. So if you decide to start a podcast and you start working on it for a while, you will develop a passion for it and you get good at it and you like it. And the same is true for anything. So I'm not afraid of working in robotics or elsewhere. I can just as likely go into marketing now with a lot of confidence from the PhD that I can do anything. And maybe I'll fall the first few years, but then I'll get on my feet and I think I'll do a good job. And I think this is one of the good things of having done a PhD where you, for 4 years, do something that you have no idea about.
Mm.
You know that you can learn and you can be better.
So what is next for you?
At the moment, I'm working for a company based in Bristol called Kinesi
Hmm.
Robotics, and I'm working on basically all things robotics, computer vision for robotics, simulation. We're developing robots for warehouses. It's really fun, really dynamic.
So you also did an internship at Amazon. Can you tell us what you got up to there?
Yeah, so it was a great experience working for Amazon. The team I was working on was working on this item picking robot. So basically, in the Amazon warehouses, you have robots bringing objects to some stations where humans are taking the objects, putting them into totes, so they're sent off to your address. And they're working on item picking robots. My internship was focused on reducing the amount of object identification errors. So basically, when the objects come to the station, you see the objects and you need to identify what is this the object that you're looking for? Is this the object you want to pick? And to be fair, like their approach was already quite good. And then I suggested that we add multiple viewpoints to this. So basically, we have multiple external viewpoints of the object while we're picking it from the bin, and we can with more confidence identify whether we are picking the correct object or not.
Hmm. I imagine there's no shortage of training data at Amazon.
NDA. I cannot disclose this.
All right. Um, uh, okay. So were there any moments when you were studying robotics where you discovered something that really surprised you, or a robot did something that was very unexpected?
Yeah, so what really surprised me is exactly these large pre-trained vision models, especially like Dino VIT, which is fully self-supervised. It worked out of the box in finding meaningful correspondences between object parts, even though they weren't trained for that purpose at all. So I
Hmm.
initially expected that we would have to fine-tune and or train models specifically for robot tasks using 3D data and detailed supervision, but instead we had these models that are able to generalize semantic part relationships, just like matching the spout of a teapot to spout of a jug with no task specific training, and that completely changed how I thought about model design. It shifted my focus away from building everything from scratch and towards building systems that can flexibly query and recombine existing knowledge, which is more scalable and honestly, it's more exciting too.
Yeah, it sounds like a huge game changer with a lot of research problems. If well, if you don't even need to fine tune, if it works out of the box, that's incredible.
Yeah,
So what was the secret to your immense productivity during your PhD?
I don't think I was as productive as you may make me out to be. I only three of the papers that you mentioned were part of my core PhD work,
Hmm.
and there's a fourth one that is currently being reviewed. Three of the other papers were my students, and six are of colleagues, and one was like a main contribution where I'm a main contributor but a collaborator. So I guess the success that can be called success, I guess, is largely due to the initial network and opportunities that my supervisors exposed me to and the guidance that they gave me. As far as it comes to me, I guess I was always very principled and I was always planning my time very well. If I looked back on my initial Gantt chart for my first year of my plan, and I followed it pretty well. I didn't even like once I wrote that chart, I didn't follow it. I didn't try to follow it that much. I forgot about it. And then when I was revising my PhD and writing the dissertation, I looked back on it and I found that actually I have followed this quite well. So I had like my own goals and I did my best to reach them. I wasn't afraid of simplifying or pivoting my research if needed, if my approach seems too complex. I think a lot of people get too hung, like they want to really like finish this thing that they believe in, and that leads to much higher quality work but much longer work. So I
Mm,
wouldn't say that I'm more productive or less productive than other PhD students. I think I actually really admire people that manage to not succumb to the pressure of publish or perish, and uh, follow through and focus on large scale projects that they believe in, and then it turns out that they work. I thought that that's a bit too scary. I want to know that even I um if I fail some project, that they have enough for the PhD to finish. So my
yeah.
idea was, okay, get some things out that are innovative and interesting, so that I can then safely focus on what I wanted to work on.
Hmm. Hmm. So is it a very collaborative research environment in the robotics center?
Uh, in a way, yes, because a lot of universities have like robotics research, but they don't have robots. While UCL has a lot of robots, so often you would have people reaching out that have a particular method that they've developed that works in simulation, and they just want to deploy it on a robot. And in that, when you start working with them, my task was, for example, a few times was I had to basically deploy their models on a robot, which often it starts off like the collaboration starts off like, hey, this thing is ready, like it just needs 1 day or a few days of work and it will work, and then we can just add your name on our paper, blah blah blah. But then in the end, often in robotics, I think it's generally the case. Nothing goes as smoothly as planned. You always take more time than needed. So usually these 3 day collaborations ended up taking 1 month or 2 months.
Yeah, the real world is messy.
Yeah.
So what applications in robotics are you excited to see in the coming years?
Oh, I'm most excited about robotic systems that are phasing out jobs that no one wants to do. The dull, the dirty, the dangerous, and also robotic systems that enable new workflows. So workflows that we didn't have access to before. In that, I mean, for example, replacing single-purpose manufacturing lines with multi-purpose mini factories that are closer to consumers.
What does that mean? Single purpose versus multi-purpose?
So you can imagine like when any car brand wants to make a new model, right? They need to
Hmm.
make custom machines that press the metal in a particular shape, and they make these very intricate factory lines that are specific for that model. And often
Hmm.
after that model is out, like is decommissioned, it's no longer sold, that whole factory is obsolete. Like it's hard to readapt it.
Mm.
Um, and there are like now more approaches that are more multi-purpose. So for example, there's a startup in the US called Machina Labs, I think, and they're working on introducing this process of roboforming. So they have two robots pressing a metal sheet from both sides, and this allows them to shape it in any shape. So basically, it allows manufacturers to ask for custom parts and get it maybe the next day. I don't know exactly what timeframes they're working on. So that's one
Hmm.
example of this. And particularly, I'm excited for about technologies that are moving the logistic centers of the world. So anything that reduces climate change, that makes our, like at the moment, I think we are sending a lot of raw materials, let's say, to China, where they're manufactured in a particular way. They're sent somewhere else, assembled. They're sent somewhere else, assembled in a different way, and then sent to the consumer. If we could move these things closer to where they're needed, where the consumers are, we would save so much on pointless emissions flying to and back and from different places.
I see. So if you have specialist factories, then for one for each purpose, then you need to send the parts on from factory to factory to factory to for processing. But if you have factories that have more general purpose robots that can accomplish many tasks, then the part can stay within the factory and undergo most of its processing within that single factory.
Exactly. Yeah. So maybe it's a bad example, but recently there was this company Arrival that is now bankrupt, unfortunately, for not reasons related to the method, but other reasons. But they were developing these mini factories in the UK that were supposed to build electric buses,
Hmm.
and the concept of having a factory that is here rather than like halfway across the world is, I think, pretty good for the world, because yeah, you're reducing emissions, you're reducing all kinds of dependencies. You're not deadlocked when there's a ship that wrecks the straits between Africa and Asia, um,
The Suez Canal.
the Suez Canal. Yeah.
Any other applications you're excited to see?
Yeah, sure. So I'm also very excited to see the democratization of robotics. So making the entry barriers lower than ever with cheaper hardware and model improvements that allow us to learn to teach policies with less data. So, for example, Hugging Face is now selling very cheap robots. There's some Chinese robots that are sold for very cheap as well. So that allows a lot more universities to get access to robots and develop things, and it will spur innovation much more quickly, which is exciting.
I remember there was a similar hope around 3D printing that once you can print anything you want at home, including a 3D printer, then you can have you quickly have abundance, provided people can just afford the raw materials.
I can tell you that in robotics, it has spurred innovation. 3D printing. There are so many approaches that have come out in the last few years that are based around our ability to quickly prototype specific grippers. For example, they now make some custom fin grippers that have these fins. So
Hmm.
they're 3D printed, but they're flexible, so they're kind of compliant when you're grasping something. They're wrapping around it. So these sorts of innovations would not have been possible without this 3D printing innovation.
Interesting. Okay. Um, and then what kind of things are you worried about that might happen in robotics?
I think my worries don't come so much from robotics; they come more from AI. And I think robotics, while robotics is and has always been replacing low skilled work at a gradual pace. So you cannot scale robotics as uh like just like releasing ChatGPT. This is not how it will work.
Hmm.
Robotics replaces work very gradually, which allows people to requalify, to adapt, to change to different professions, to find like figure out new work. So this is what happened with the washing machine, with the dishwasher, with the printing press, etc. What worries me more is AI without the embodiment. So the AI that's replacing the high skilled work. But that's, I guess we'll see what happens there.
Yeah, software can be rolled out practically instantly. It's just a matter of how quickly can industries or businesses adopt it. Whereas robotics, yeah, you have to actually build the robots and send them out, and that takes time.
Yeah,
Well, it's been great talking to you, Dennis. I've really enjoyed it, and I've learned a lot. Thanks for coming on.
yeah. Thank you very much.